We want to describe here a personal speech recognizer which can be adapted and trained easily to any accent or language. The recognizer is based on a novel algorithm called RISC, which stands for Recognition by Indexing and Sequencing. RISC was invented and patented by Professor Jezikiel Ben-Ari. Here we want to mention some important features of our speech recognizer. At first, our speech recognizer can be easily trained to each user, unlike recent widely used methods. Because of this adaptability, our recognizer makes much less errors. The recognizer can be adapted to any language or accent, and it has a parallel classification structure which makes the recognition even faster. In the next few slides, we will discuss some experimental results that we achieved using our RISC method for continuous speech recognition. In this example, we try to recognize the sentence, "I would like to eat some pasta." The sound waveform corresponding to each word, along with the time extent of each word, is shown on the top of the figure. Each word in the sentence is represented by a unique color for better understanding of the result. Here, I is represented by blue, would is represented by red, like is represented by sky blue, to is represented by orange, eat is represented by dark blue, and some and pasta are represented by yellow and green respectively. We show here 7 score graphs, each for the RISC matching score of another word exemplar. The score graphs are in the same colors as the words they pertain to. From the graph we can see that all the words are identified correctly by their score peaks. The score graph corresponding to each particular word got the highest value at the exact time and location of the word, which means perfect recognition in this case. In spite of recent success of some state-of-the-art speech recognition systems, there are some major problems incorporated with those methods. First, these systems make a lot of errors with users who have non-native accent. Second, these systems are very difficult to adapt to different persons. Third, these systems have training procedure which is complex and time-consuming. And at last, slow recognition is another major drawback of these methods. Keeping all these problems in mind, we set our goal to build an adaptive system for personal speech recognition. We mean a system that would be easily trained for any user with any accent in any language. A system that would require only few samples to be trained. A system that also would have higher reliability in recognition compared to existing popular systems. And finally, the system should be faster. Such a system could be applicable for numerous practical purposes such as personal cell phones, speech and voice recognition based applications on computers, for communication with non-English speaking patients in hospitals, and in voice-controlled cars. We would like to mention that our motivation behind the idea of building such a system came from the need to communicate with patients who don't speak English or elderly persons with speech problems. This system could help the hospital staff to understand how these patients are feeling and what their requests are. Here are some basic steps of speech recognition which are illustrated by a flow diagram. At first, as we all know, speech signal is recorded by a microphone, which is converted into an electrical signal at the same time. This signal is then transformed to frequency domain by using fast Fourier transform. Next, every sample in the frequency domain is a set of numbers that are represented by vectors. After that, the total speech signal is transformed into a temporal sequence of vectors. Finally, these vectors are used by the speech recognizer algorithm and consequently classified into words. On the left, we see a flowchart representation of the steps of extracting the vectors which are used by our speech recognizer. At the first stage, speech signal is sampled at 16,000 samples per second. The high frequencies in the sampled signal are then emphasized using a pre-emphasizer. Next, sets of 205 samples in overlapping windows are transformed into Fourier coefficients. Next, the amplitudes of the Fourier coefficients are filtered by a set of Mel filter banks. At the very next stage, the logarithms of the outputs of the filters are transformed using cosine transform. Finally, 13-dimensional vectors of the cosine transform coefficients are found. These are called Mel frequency Kapstrom coefficients, or in acronym the MFCC. In the next few slides, we shall discuss the methodology of our speech recognition system. Our algorithm is called RISC, which stands for Recognition by Indexing and Sequencing. Basically, our RISC is a method that measures similarity between two sequences of vectors, the input sequence and the exemplar sequence. Exemplar vector sequences, which represent the training words, are stored in a data structure just as shown in the diagram. The RISC algorithm finds the optimal bipartite graph matching between the input vector sequences, which represent the input speech, and the exemplar vector sequences. The links you see in the diagram indicate the similarity measures between samples of an input sequence to samples of an exemplar sequence. RISC finds the optimal match which has the maximum aggregated weight of those links while fulfilling the requirement for sequencing, meaning the requirement for temporal ordering, which will be elaborated in slides 16 and 17. Here is the RISC methodology in brief. In its training stage, RISC stores all the exemplar sequences in its multidimensional data structure. Then, in testing stage, RISC finds the sequence which has the highest sum of similarity measures by a dynamic programming optimization algorithm. As already mentioned, The optimization must fulfill the sequencing constraint, which will be described in detail in slides 16 and 17. So, what is the aim of optimization that we mentioned? First of all, we have a sequence of vectors of the input utterance, and we have many stored exemplar vector sequences, each representing an exemplar word. Next, using indexing, we first find for each vector in the input sequence all the similar exemplar vectors by finding the nearest neighbors to each input vector. Next, we search for the exemplar vector sequence which has the maximum sum of similarities to the input sequence. This exemplar sequence is recognized as the word uttered at the input. We have to mention that each input vector has various amounts of similarity to all the exemplar vectors, but only the ones with the highest similarities are selected. Each such similarity is represented by a link shown as blue arrows in the diagram. The objective of optimization is to find a stored exemplar sequence with a set of links with maximum total similarity while fulfilling the sequencing condition. The input utterance is then recognized as the most similar to that exemplar. Here we want to discuss sequencing, which is a basic part of our approach. Optimization and sequencing are very similar to optimal weighted bipartite graph matching, but with an additional temporal ordering constraint that must be followed. The sequencing is simply a requirement to keep the timing order in the links. It means that an earlier and a later samples in the input sequence cannot be linked with the later and earlier samples in the exemplar respectively, and vice versa. For example, in the above diagram, links with 0.8 and 0.7 cannot be combined in the total summation, as they break the sequencing constraint even though they give a total highest similarity measure. Our sequencing algorithm must take the links with 0.8 and 0.5, as they maintain the temporal sequencing order and have the highest total sum. At this point of our presentation, you may think that our method, RISC, is similar to dynamic time warping or DTW method of speech recognition. But RISC is very different in the principles of methodology used and in the implementation. As a result, RISC provides much better result compared to DTW. A brief explanation of DTW along with its differences with our RISC method is given in Appendix 2. A detailed explanation of our RISC method along with an example of sequencing and dynamic programming is included in Appendix 1. A general description of the most popular speech recognition method called Hidden Markov Models, or HMM, and its comparison with our method is discussed in Appendix 3. We are showing now the receiver operating characteristic curves, or ROC curves, of risk versus HMM. ROC curves are used for standard quality measure of recognition systems. On the vertical axis of the graph, we have true positives rate, which is commonly known as recognition rate, and on the horizontal axis of the graph, we have false positive rate, which is commonly known as false alarm rate. The area below the ROC curve measures the quality of the recognizer. Higher area indicate higher quality. We compared 3 different versions of a risk method with Sphinx, which is the state-of-the-art speech recognizer based on hidden Markov models. From the ROC curves, we can see that Sphinx, which is denoted by the dotted red line in the graph, achieves lower recognition than our risk algorithm. And this pretty much completes our general discussion on our speech recognition system and its methodology. For the rest of the slides, we will discuss more detailed representation of our risk method in Appendix 1. Then there will be a brief discussion on discrete time warping and hidden Markov models and their comparative analysis with our method in Appendices 2 and 3 respectively. This is the end of my presentation. Thank you for listening to this presentation.